Hi everyone, this is Adam Green here from ATA Engineering, and welcome to this ATA webinar of system simulation of urban air mobility aircraft. I'm your host today, Adam Green from ATA Engineering, and with us we have Scott Kidney, also from ATA Engineering.
Hello.
Thanks, Scott. And so before we dive into the full webinar, really where Scott is going to be presenting some technical details on Amesim and other tools, I'm going to cover the basics of who are ATA Engineering, coupled with an introduction to Amesim. So ATA Engineering are an employee-owned engineering consulting group. We have around 200 people, and we're a very skilled bunch of folk with over 140 degreed engineers, many PhDs and masters in the group. And we really tackle mostly the hardest problems in various industries, including aerospace and defense primarily, but also robotics and controls, themed entertainment, industrial mining, and also some consumer products. And what do we do? Well, we really do engineering consulting in various methods, one through design, analysis, and especially in test. And we have offices throughout the US, mostly in the centers of aerospace activity. So on the West Coast, from San Diego, LA, and San Francisco, in the middle for Denver and Albuquerque. And then further east, we have Huntsville and Washington, DC, both areas of aerospace activity, obviously. And ATA are also a full platinum partner with Siemens software. So we sell and support pretty much all of the Simcenter portfolio of tools, including Star CCM Plus, Amesim, FEMAP, NX, Nastran, really all of the Simcenter portfolio. We have experts sitting ready to help both support and do services work if needed. So moving on to really what is Amesim, the focus of today's presentation. And first of all, Amesim is part of the bigger Simcenter portfolio for Siemens, which includes 1D controls and really where Amesim sits in the portfolio. But other tools in that include more higher end tools, including Star CCM Plus for CFD and other 3D tools, together with physical testing as well. And so Siemens has built this infrastructure of basically being able to share data between tools and really build up this very complete portfolio where many of the tools can work together to provide an end-to-end digital twin solution. So it's a very compelling solution for really the full production and development suite of really any product. And so Simcenter Amesim is a 1D simulation tool primarily, and it's really designed, especially in the aerospace sector, so to model really any part of the industry with its general physics models, and it can really tackle airplanes, unmanned vehicles, helicopters, really any part of the aerospace industry is applicable to model with Amesim. And really, what is it? Well, it's a scalable multi-physics modeling analysis product that really uses 1D modeling to make multi-physics models that are not only accurate, but also very fast to run. And so the areas of application include flight controls, flight dynamics, environmental control systems, all the way through the list you can see there. Together with the disciplines below for fluids, thermodynamics, energy, and flip control and mechanical, etc. And so it's really the complete tool that lets you tackle almost any problem in the aerospace sector completely in a 1D modeling scenario. Not only that, it also has connections to other tools in the industry, Modelica and the FMI interface, connecting to Amesim, as does MathWorks, so that you can really connect it to other tools that you may already have. So it's really a complete tool to be able to do simulation in this space together with connect to any other tools you may have. And not only that, it has a complete set of dedicated tools within Amesim specifically for the aerospace industry. And so in this scenario, you can see we may have a flight mission planning scenario on the left. and an Amesim model in the center. And really running through those different scenarios lets Amesim evaluate all the conditions for that scenario, and really look at the results and create a model with an improved performance. And so along the bottom, you can see some examples of subsystems where that could be used, from landing systems to flight control. Amesim has been used in all of these areas. And one of the things that really the connection with the rest of the Siemens Simcenter portfolio gives you is the ability to automate processes. And in this case, you can see in the middle there, in the center is an Amesim model of a helicopter refueling tank model, but that is controlled with a HEEDS model to actually do process automation to control Amesim, together with analyze the results. And one of the great things about Amesim is that most of the models can run very quickly, and quickly as compared to, say, CFD or other higher fidelity tools. But certainly each point in a simulation for Amesim can run in, from seconds to a few minutes. It's certainly not hours or days like it can be with CFD. And so to automate that, if you wanted to evaluate 1,000 different permutations of a refueling tank system for a helicopter, HEEDS will let you automate the process, and Amesim can do the actual physics to help you really drive the design to something more advanced than you started with. And so when you look at what you can use Amesim for, it's been used a long time in the industry and aerospace. And 2002 is this early example, but it actually goes back further than that. And you can see the Amesim layout here, the 1D model of an aerospace liquid rocket propulsion engine, which is really quite a complex physical problem. But Amesim is able to break it down into 1D nodes and really tackle the problem very cleanly. And then as Amesim has developed, this was in 2002, then a revised version of the same model was rerun in 2007, this time making it a fully transient model. So really the point is that Amesim can be used for complex physical scenarios that really need something simple and fast to model to get answers quickly. It's another example of a pressure valve for an aircraft braking system. Typically, hydraulics and pressure systems are very easy to run in 1D. They run very quickly, and also are very accurate. So Amesim is very well suited to run this kind of scenario. And then even looking at a more complex system, which needs various models from the mechatronics of an environmental control system through to the batteries, through to really every part of the system, Amesim has different models to control all pieces of it. So when you've got a blended system that blends mechatronics, mechanics, and electronics, Amesim can also handle that. And again, as we move forward in time, you can see the models are getting more complex. This one is for a flight control electromechanical actuator done in 2016, and you can see the actual Amesim workflow is getting more complex, but still attainable. So here's a few examples of some customers that have used Amesim in real world examples. This is Leonardo Aircraft, and they used Amesim to actually optimize the air conditioning architecture within their aircraft. And really, we've talked about that already, but the point is that down here, one of the owners of the company basically confirmed that modeling gave them sufficient accuracy, but they were able to do it very quickly, and so they were able to evaluate lots of different examples and come up with answers within an accuracy level that was acceptable to what they needed, to get things done quickly. And clearly, if you need to go to high fidelity models, you can do later, but certainly running Amesim earlier in the design cycle can get you very close to where you need to be from a design point perspective. And then more recently, Siemens E-Aircraft were developing a full electric motor driven aircraft, and Amesim was used to model really all pieces of it. And you can see in the center here, there's a fairly simplistic model of the engine, the generator, the motor, and so forth. But each one of those could have a more complete sub-model inside of Amesim controlling those features. And so as you can see from our client here, Basically, they could only develop such power density because they used Amesim for the very beginning of the development cycle. And so we know Amesim is a 1D simulation tool, but what makes it so useful, and one of the things that really separates it in the market from other tools that are doing 1D simulation and network modeling, is the availability of templates. And so when you used Amesim, it comes with a complete set of models and templates to use in your industry already. So for aerospace, it comes with a complete set of templates to do motors and to do actuators and really all the things you might want to do. And this really sets it apart from the likes of, say, MATLAB, where MATLAB technically can do similar things, but you end up having to create all of these models from scratch. And so Amesim can really accelerate the deployment of this technology by using the built-in templates. And in fact, there's over 90 templates for the aerospace and defense sector within Amesim. There's a lot of other libraries too. The number is much higher than 90 across the board, but for aerospace, it really gives you a complete set of templates ready to go and build models very quickly. So with that, I think I'm going to pass the ball to Scott. Scott, are you there?
Yes, I'm here.
Excellent. So thank you, everyone. Scott, if you can take the screen share, and over to you.
All righty. So how do we use Simcenter Amesim? So just to kind of paint a picture of where does it fit into the product development process, it resides in an area that you maybe typically, above this, you may use Simulink or MATLAB or other methods to model, at a higher level mathematical way, the products you're developing, or between, of course, 3D CAD, CFD, FEA, where you're actually working on components at the component level and developing and analyzing just individual parts. Amesim can reside in between these two areas in your product development process, where it really can take a look at the big picture of system, subsystem, and component engineering. What's really neat about Amesim is that it has a multi-level nature to the definition of models. And you can really do it 4 different ways. The first way would be a functional model. For example, here we're going to be taking a look at a check valve where it does have a component library which you could go into and simply select this check valve model and drop it into your sketch for the system and continue on with your modeling. Next would be, if you want to have more information or a clear picture of, say, maybe a check valve chattering in a fluid flow for some reason, you could actually, instead of just using a check valve, actually model it with a discretized spring, a mass, the valve, and of course the fluid flow around the valve. Another option, of course, is just using almost like a block diagram, similar to what you would see in Simulink or MATLAB, with blocks representing how do different areas or different regions of the valve work mathematically, and then what's the flow of information through the schematic. And the fourth way that's available too is modeling with a software such as programming language such as C or Fortran or Modelica or even Python. So a lot of different ways to model your project are available to you within the software. So there are many uses for modeling with Simcenter Amesim. The system and subsystem modeling becomes more valuable the earlier you start it in your project, and then of course continue it and further develop it throughout the whole project. It really gives you insights into the final way the subsystems or systems will operate as more and more fidelity gets poured into them. Overall, the primary uses of the model could be such as these items listed here as far as systems architecture, trade studies, specification definitions, parameter studies, troubleshooting, control design and verification, initial control tuning, and model verification. So today, what we're going to be taking a look at is going to be trade studies, control design verification, and initial control tuning. But as if you take a look at ATA's YouTube page, it'll go into some of this area, other areas that we've shown in previous webinars. So just taking a look at the overall distributed electric aircraft model that we're going to be showing today, it's really broken up into 5 different parts. As far as a rotor dynamics section, which we've covered previously. What's new are really the battery section, which is shown in the middle of the schematic, the low voltage buses at the bottom of the schematic. And then looking at the right here, we still have a very simple flight dynamics and control section that's a carryover from previous work on this model. And then a new tilt motor model that we're going to be looking at today, just to illustrate adding fidelity to a specific operation within the model and seeing how that compares from just a signal used to control an input or an angle change on one of the fans to actually a motor controlling everything. So again, it's really an increase in fidelity from the previously shown model. I'm going to get going into it. First, we're going to discuss the low voltage battery bus, and then the tilt motor modeling, and then last, a trade study on the tilt motor control parameters, and just showing trade studies with respect to various control parameters. So let me switch over from the presentation over into the software. So again, in the software, where we last left off, we did have a UAV with 4 fans, 4 motors, and of course a control system for flight that was shown. And there, like I said, too, is shown previously. You can go into ATA's YouTube channel and find this video from previous UAV modeling, and I'll go through some of it. But then what we've added below that is all new as far as the low voltage buses. So let me just first start with how does the software work. So we have a sketch window in the middle here, and then a set of menus on top, and various panes of information that come up on the right-hand side here. There's really 5 major stages to modeling. First would be sketch, where you do have the schematic that you can see for the overall model. And that's accompanied with a model tree off to the right-hand side here. The purpose of this is to really find components, drag and drop them onto your sketch, and link them up into some sort of schematic. So for example, here would be a resistor and a switch. So here would be a switch. You just simply drag and drop it into position. It shows up differently because it is unlinked to the schematic versus the one shown to the right here is linked up. Same thing for, say, a resistor. You can just drag and drop it into position and then bring it closer to a switch. You can see 2 green nodes, simply links up. These are still shown differently because each end is unlinked from the schematic, but as you link up more and more devices, they change colors from how they're shown here to how they're shown on the right. From there, we can move into submodeling. So a lot of these various components have different submodels associated with them. And what I mean by submodel is just a different configuration of the model. So a resistor, for example, is just a simple resistor, but a switch, sorry, it's also a switch. Let me see if I can find one here. But it allows you to set, many of these components will have just different options available for each of the, for the different configurations that could be selected for each particular component. Parameters is going to be the third stage of modeling, where you can actually, for example, for a resistor, set the resistance or various numerical models associated with each of the components in your schematic. Simulation. Simulation is really where, once all the parameters are set, the model's set up how you like it, you can go in, it compiles first the entire schematic, which is just kind of getting it set up, and then you have various choices available to you as far as running a simulation, setting up parameters, and then also, of course, this is where we can set up trade studies as far as you looking at components, parameters, and iterating on them. We'll take a look at that later in this presentation. And then finally, the fifth stage of analysis is post-processing. So we'll go through just a couple different options available to you to look at data once it's all processed. Okay, switching gears from just an overview of Simcenter, just what parts have we actually looked at adding, or what we've actually added to this model would be a DC-DC converter coming off of the main propulsion bus and main propulsion battery to a low voltage battery, and then on to many different levels of low voltage equipment such as lights or avionics, etc. This could be any number of different things that may be in your UAV. And just to kind of show, the various levels of increasing complexity of a model, this first example on the left-hand side is the easiest as far as complexity. It's very simple. It's based off of a time-based actuation of switches, which starts at time 0 and then runs out to 125 seconds. And what happens is it goes through a transmitter. That transmitter is then fed into the switches as far as when do they get toggled on or off. And then that controls the flow of current. So that each resistor, depending on its resistance value, this would be 1 ohm, this is 10 ohms, the flow current happens through the resistor. So this could be a model, the time is based off of when your UAV is in the air, what's happening at the different stages of flight, and then the resistance could be any number of different pieces of equipment on your UAV, such as lights or cameras. If we're talking like a larger, larger UAV that may be used for moving people, of course, you're looking at cabin control, etc. So, but this is just a simple time-based switching of resistors on and off, just to get an idea of what's happening maybe through a full set of phases of flight. Another option, just moving up in complexity, would be, as I move over to this electrical bus here, is it's very similar what the GL components stand for, just a generic DC load, but it's based off of different phases of flight. So at the top of the schematic, you can describe different aircraft missions, and this is originally created with the intent of like a winged aircraft, but it could be applied to any number of different aircraft, such as helicopters or UAVs, and that's what I used here. But it's has a number of different stages as far as an initial phase, and so on. Each phase does have a number to it. So this would like taxi out as phase 3. How long does it go for, or how long does it last? And then also, you know, like takeoff. How long does this next stage last? And what's the altitude at the end of it? So you can use this series of phases for this particular aircraft mission, and then go back into your modeling here and define what's going on as far as, back this down just to parameter definition, you know, what's the, if it is actually being used for that particular phase of flight, and what's the value being fed into the general DC load for the bus, and then what's that load on the entire electrical system. So from there too, one thing that you can also do is, once you have the various loads modeled and their sequence is being run such as it typically would be with a typical aircraft mission, you can add components such as wires and do wire sizing. And this is a great example here that, you know, I added in a wire. I've run a simulation, and just to take a look at, you know, with all the various loads and information, you know, generated from an analysis, I'm going to switch to the simulation menu, click on the component, and just look at the output current. Simply holding that value, dragging it into a sketch will create an automatic graph for me, so I can see throughout the entire mission, you know, how much current is going through this particular wire, and for cabling sizing, etc. Beyond that, the way this can be defined, I can actually get various temperatures as far as insulation material temperature too, based off of the current. This is obscenely high, but it's just based off of the basic parameter set for the wire. But you can go through and set up using a wire application manager of what's happening within this wire due to various pulses of electricity or current draws of electricity, and it'll produce a model with specific, I guess, conductor performance based off of all the information that you can feed it from either your own testing or manufacturer testing. So really going from a simple, you know, a simple just connection originally with no resistance to an actual cable with insulation, and what's the proposed, or what's the expected temperature of the insulation that might be seen. You can see just, you know, how easily and rapidly you can increase the fidelity of your model just by adding in more and more information about what's happening with perspective or respective systems. Okay. So moving on from discussing low voltage buses. Previously, we showed in an analysis here. Just going to switch over models. When we did work in this area last on a webinar, we showed how there was just a real simple flight profile used, and you know, we had 4 propulsion motors, 4 ducted fans, and ran the analysis. We did show that, you know, we could bring up and set up a simulation of the analysis, which showed that flight profile and what was happening with it, and really give you some graphical output of what's going on. So taking that one step further, the way the ducts move is controlled by this angle theta, and what we did for this particular example is we took away just the control signal from the control laws over here. It's specifically Y2 in this one example. So instead of having Y2 going in here, we actually took that away and created a tilt motor model with tilt motor control. And this was just done as simply as just dragging on from Sketch, you know, a motor. And you can find motors just by typing in motor and then going down to and finding the specific motor you may want to use in your particular analysis, dragging it on, Control R to get it oriented the way you would like, and set up a motor, a reducer, and then with the reducer, we're feeding back both theta, which we ultimately send to the ducted fan, and the speed that goes back into the control for the tilt motor. So putting this in and running the simulation, let's switch this back over to simulation mode just to get graphs going. You know, I can click on the motor. I can look at you know, what torque is being applied by the motor throughout the flight, and use this information to start sizing motors and gearboxes and cables, etc., and making sure my motor selection is accurate. And then also too, what's kind of interesting is you know, how good is this really performing, and really take a look at with just a general system, what is the tilt angle based off of the motor, and comparing that to one that's just receiving the signal. And you can see, you know, it's relatively close, but then you start seeing some of the dynamics and other effects of an actual motor and gear head system versus just a signal of what's happening with respect to the applied signal to the ducted fan as far as tilt angle and everything. So this is, of course, just a real simple, you know, motor and control system. But, you know, early on, you might want to say, okay, I have these PI controllers on the tilt motor. I'd like to actually iterate on various parameters with respect to this. And what you can do, I'm just going to show this quickly once again, as far as, you know, how do we set up various studies or trait studies with respect to parameters and control systems, but it's simple as just dragging and dropping that into our study manager parameters window, and then shifting this over to, you know, what kind of study would we like to run. As far as here, we're starting with an initial value. I'd like to actually run this with a step size of 50. We're going to go one under, so we start a value of 50, and then we're going to go number above. I'd like to run this all the way up to 200. And this is just a simple varying between two limits of a simple parameter, just to see what does that do with respect to commanded angle. There's a lot of other options available to you too, as far as a design of experiment, Monte Carlo, or different types of optimization. As you create them, it'll store them in the setup here, and you can choose what you'd like to run, of course. So once you have your studies all set up, you can then go to your run parameters, and instead of doing a single run, you simply have to do batch. And then you would have to actually, you could see using your design matrix what your various runs would be. I have a feeling here that this is a little bit different just because I did put this in here. that's okay. Anyway, so setting up a batch run is as simple as that. And what I wanted to show here, I took a slide of this, and I'm going to bring my slide set back up here just to show it to you, was once I set it up and I had the 4 runs set up with 50, 100, 150, and 200 for the control proportional gain. I took a snapshot of this because I couldn't capture it just because of the different models I'm cycling through. But the 4th one failed, and the first 3 did solve. So I wanted to really show the robustness of the solver built into Amesim. What's really great about this is that, you know, even though the solve did fail out, there's a lot of information here that you can go into and take a look at what's happening. So we just wanted to illustrate and show that. So this is the model with the solve that's been completed. And you can still see, you know, if I want to take a look at the angle with the propeller, this is just using the first solution. But if I bring in all 4 curves, I can see that, you know, there's definitely the 4th one is going out of control. That proportional gain is just too large. If I take that off the table, take a look at what else is going. I can see with the various solves, you know, number 1 is, remember, the gain of 50, you know, low smooth, some bumps and everything, but even if I increase the proportional gain up to 150, I can see chatter in that signal. You really would be desirable in the aircraft. So you can see initial control parameter sizing, what's going on. But you know, you can also see too, you know, just from the graphing that information was stored. You can kind of see what's happening as far as with the parameter and your angle, what's not desirable. The other thing that I thought would be really neat to see is this is an animation set up for that particular analysis run. And you can see how just that parameter in this 4th analysis, it goes unstable just because the gain is too large, and you actually can see that in the animation and give you, you know, give you feedback about what's exactly causing your run to terminate. But you know, just a lot of good information even from a failed analysis. So. So switching back to slides for the moment, you know, what could be improved even further? Again, it's Amesim is really you know, a software system that you can you know, start very simple and just drag in very simple components such as resistors and switches and start your modeling to, you know, get an idea for, you know, we showed conductor sizing today. Any number, you know, just basing draws and, you know, battery sizing, etc. But you can iterate and add interactions to, you know, based on what your needs are, and just increase the fidelity of the model, even as the project matures, and once decisions are made in the design process, you know, put them back into your Amesim model, and just make sure maybe some of your early on assumptions still are true and hold valid. Actual performance data can be used to dial in components. Today we showed, you know, motor information, gearbox information, even wire, manufacturer wire data. Your own test data for wires could be pulled into the model so that you can get accurate temperatures or performance, etc., into your, you know, dialed into your models. You can customize control algorithms and do some initial algorithm design with the components built into Amesim, just to progress and have a good idea where to start with that before maybe you want to attempt more complex algorithm design in something, say, MATLAB or Simulink. And of course, you can perform trade studies on any number of different parameters, from control parameters, motor parameters, etc. It's just as simple as I showed you, dragging and dropping in various parameters into a field, and then setting up a solution to iterate on those values. So Adam and Jonathan, that's my last slide. Turn it over to you.
Excellent. Thank you, Scott. Jonathan, do we have any questions?
Not yet. So yeah, I would encourage everyone, if you have questions, feel free to put those in the chat, put them in the Q&A tab, and I can read those in. You can also, if you would like to, request permission to be unmuted, then I can grant that as well. And you can ask Scott or Adam a question. And maybe while some of those questions are coming in, Adam, I think this might be a good opportunity to sort of talk about ATA's next webinar. Do you want to share a little more details about that one?
Yes, our next webinar is going to be using HEEDs in the same industry segment as in urban air mobility, but using HEEDs to automate design processes. And so that's going to use Amesim a little bit, but it's probably going to use other tools as well. And that's going to be on December 17th. So a week tomorrow, 2 weeks tomorrow, at 1 p.m. will be that webinar. And that'll be with myself and some folks from Siemens as well, to really show using HEEDs to automate processes, to find optimized designs in amongst the design space using Amesim and other tools.
Awesome. Yeah, I'm looking forward to that one as well. We're going to send out an email in a day or two once we get the recording of this webinar posted, and I'm hoping to have the registration page for that next webinar included in that email. So keep an eye out for that. Still happy to accept any questions. I don't see any yet. So Adam, I might turn it back over to you to wrap up, and please, either now or after the webinar, feel free to reach out to us with any questions that you do come up with.
Excellent. Thank you, Jonathan. And just to note that this webinar will be posted on ATA's YouTube channel. So if you want to revisit this and look at any of the details that Scott presented, feel free to go and look at those YouTube videos at your leisure. So thanks very much. We will wrap up. Thanks for attending, and have a good afternoon, everybody. Bye-bye.